So we just looked at this example of sort of starting to think about angular momentum, right? We started with this sort of definition that said the angular momentum of a system is simply the sum of the position vector of each particle in the system crossed with the linear momentum of each particle in the system. So that's a definition of angular momentum. And we looked at this particular system that we said was rotating in the xy plane with an angle theta, so it has an angular velocity of simply whatever that angular velocity is in the k-hat direction. So since it's rotating counterclockwise, angular velocity is coming out of the page. And we went through a bit of a calculation to figure out what the position and the velocity and the momenta of this particle and this other particle were, in order to figure out that for this case, the angular momentum of the system was equal to 2 times m times r squared times omega in the k-hat direction. Okay? Now I want to make an observation about that, which is that we could rewrite this as 2 times m times r squared simply times the angular velocity vector, right? So in fact, when you've got this object that is purely rotating, it sort of looks like the angular momentum can be written as some initial quantity times the angular velocity vector. And that's possible to do when you've got a rigid body that's actually rotating over an axis. In fact, we can see how that would sort of extend. Let's imagine that we put another mass here that I'll call big M, and another mass here that I'll call big M. And I thought about what the angular momentum, so these are maybe at r over 2, and let's say that's at r over 2. Right? Well, if I went through and did this same calculation for this case, I would find that my angular momentum of the system would actually have 4 terms in it. It had 2 last time, which is where this factor of 2 came from. I'd get an mr squared times omega for the first mass. I'd get an mr squared times omega for the second mass. I'd get a big M times r over 2 squared times omega for the third mass. This is not big M over 2, this is r over 2. And then finally for the fourth mass, I'd also have a big M times r over 2 squared times omega. Right, now there's a good reason for that, right? Each time that I look at this, I've got to have both the distance from the origin, and that's crossed with the angular, with the momentum, but the momentum is proportional to velocity, and the velocity is proportional to the distance from the origin and to omega. So I get this distance from the origin squared, one from the momentum and one from the radius. I get a mass from the momentum, and finally I get an omega out of the momentum. So in general, I could actually think about rewriting this as the momentum of the system as being the sum over all the particles in the system of the mass of the particle times their distance from the origin squared. So I'm going to say r sub I is the distance. It's actually not distance from the origin, it's distance from the axis of rotation. That simply times omega. And you can see that's what we've got here. I can pull out my omega, and then I'm just adding up where each mass is multiplied by the distance that mass is from the z-axis squared. This quantity out front is frequently enough used that we end up labeling it something. This is what's called the moment of inertia. For this rotating system, and what that tells you about is sort of how much the system resists changes in its angular velocity. So it's very much analogous to the mass in linear systems. So if we make the linear angular analogy, this quantity, the summation of the mass times their distance of the mass from the axis squared, is analogous to mass in the linear case. Let's think about another sort of simple example of that. So I've got 2 wheels, right? One is a solid wheel, and one is more like a bike wheel, right? All the mass is located out at the edge, and then it's just got very light spokes that go out to the edge. But I'll say that each of the wheels has the same total mass. And I'm going to imagine rotating those wheels about the z-axis, so coming out of the page. I'd like to know which one of these has greater angular momentum. Sorry, which one has greater moment of inertia. Well, if I were going to calculate the moment of inertia for each of these, I'd say, okay, I, which is the term for the moment of inertia, is that first term that we just had, right? It's this summation over all the masses times their distance from the axis squared. So for this first mass, it's going to be a summation, all the masses in that wheel times their distance from the center of the wheel squared. So I'm imagining taking this thing and breaking it up into a bunch of little masses and adding all of those up times their distances from the origin squared. Similarly, in this one, I'll do the same thing, except now all of my masses are a distance big R from the origin squared. So this wheel, the angular momentum is the moment of inertia is pretty easy to calculate because it's simply going to be R squared, right, the radius of the wheel, times the mass of the wheel, because all of the mass is located at a distance R from the axis about the z-axis, right? On the other hand, in this case, a lot of the mass is actually closer to the z-axis than big R. And so that implies that this solid wheel will actually have a lower moment of inertia than the wheel where all the mass is concentrated at the edge. And it's pretty easy to see why that would be the case. This mass that's pretty close to the middle is actually going to have a fairly small momentum, whereas a mass that's close to the edge of the wheel will have a much larger momentum. So the sort of total angular momentum of this thing for a given speed will be lower than the total angular momentum of the hollow wheel for the speed. So that's sort of one observation about moment of inertia. I'll make one other quick observation about moment of inertia, which is that moment of inertia depends on the axis you're rotating about. Let me give you one sort of concrete example. Let's look at this wheel case. So I've got the wheel, and let's imagine that instead of it rotating about the hub, let's instead have it rotate about the y-axis, right? So this is x, this is y. So I'm imagining like a coin rotating about the y-axis. Well, what's going to happen with that? Well, now this little chunk of mass is actually pretty close to the axis of rotation, whereas this chunk of mass is a long way away from the axis of rotation. So pretty clearly, for this case, the moment of inertia is going to be smaller than it will be when you're talking about the moment of inertia about the z-axis. So for this wheel, we would say that I about the z-axis is actually greater than I about the y-axis, and also you'll note that it's pretty easy to convince yourself that if you're rotating about the x-axis, I about the x-axis would actually be equal to I about the y-axis. So there's a couple things to be aware of when you think about moment of inertia, and there's certainly quite a bit more in Kleppner and Kalenko about how to calculate that. I think for the purpose of the video, this is probably enough introduction to moment of inertia at this point.